Cast is now starting. All attendees are in listen-only mode.
Hello everyone, my name is David Calvert and welcome to today's iFormulate Introduces webinar, which today is entitled Design of Experiments for Formulators. This webinar is being recorded, so you will be able to review it later at your leisure, and your colleagues who are unable to attend will also be able to listen in. You will receive a link to the slides and the recording 24 hours after completion of this webinar. You're all placed on mute. We have a large number of attendees today, but if you do have any questions as we're going along, please feel free to use the question or chat feature, and after we finish the delivery, then we'll try to answer as many of these as possible. You can see today's program on the right-hand side of the slide, and following the introductions, Paul Murray will take you through design of experiments and how this approach can be of benefit to all formulators. So, some very brief introductions before we get started. As I mentioned, my name is David Calvert and I'm one of the co-founders of iFormulate. And together with Paul Murray of Paul Murray Catalysis Consulting, we'll be your hosts for today's webinar. As I said, Paul's joining me today, and after graduating with a PhD in chemistry from Trinity College Dublin, Paul joined AstraZeneca as a process chemist and spent 12 years there developing his skills. His work spanned early stage chemistry with an aspect of scale-up of medicinal chemistry process, later stage development and life cycle management, all with the application of design of experiments. In October 2013, Paul established his own consultancy company, Paul Murray Catalysis Consulting, and he provides expertise globally to the chemical industry in advanced design of experiments, catalysis, and process development. So just before we get to the meat, I need to give you a brief overview of iFormulate. We're a company which is founded by Jim Bullock and myself. Between us, we now have close to 6 years experience working in the formulating industries. We've been in business for close on 6 years and bring our own experience and knowledge gained across many industries and in varied functional roles. And by combining these with the expertise of our associate partners, we can assist our clients effectively. We divide our activities into 3 business areas, and in iFormulate Consult, we carry out innovation and technology consulting, mainly in formulation science and technology for people in the companies in the private sector. At iFormulate Strategic, we've carried out and assisted strategic projects in the area of formulation science and technology for sector bodies and associations such as the Knowledge Transfer Network, the National Formulation Centre, and the Royal Society of Chemistry. Under iFormulate Skills, we design, deliver and promote training courses and programs which may appear under our own banner or may be in partnership with third parties. This webinar is part of our iFormulate Skills activities, and we'll discuss the specifics of a new 2-day training course on design of experiments for formulators at the end of the webinar. You can see further details of our activities on our website, www.iformulate.biz, and you're also invited to join our mailing list for regular newsletters. Simply email myself or info@iformulate.biz. So without any further ado, I would now like to hand over to Paul Murray, who will be taking you through the meat of today's presentation. So over to you, Paul.
Okay, thank you very much, David, for the introduction. And welcome everybody to the course, to the webinar, where I'm going to tell you about design of experiments and how this can be used for formulation scientists. So I'm going to introduce you to design of experiments and how it can be used in formulation. I'm going to demonstrate some of the benefits of using design of experiments, and I am going to go through a case study in using experimental design in a formulation application, which is to support quality by design in a pharmaceutical application. So traditionally, when you want to develop a process, you have to start with an idea. You have an active material, you have whatever other ingredients that you need to add to it, but you have to start with an idea. In chemistry, we start with a root, but you have to start with an initial idea, and then as you start to carry out experiments, usually your first experiment will not meet your objectives, so you will start to make changes to this process, and essentially we will do a whole sequence of experiments and we will walk a very long and windy road to try and get something that might work for our process. Some people at that point will, having found something that could be used as a process, may well use an experimental design to prove that process is robust. What I am going to talk to you about is how to use experimental design at every level, but actually I advocate to use experimental design where we look at all of the factors up front. So a factor is anything that we could change in an experiment to affect the outcome. So it could be the ratios of materials, or the material that we start with, or the additives, or other components. So here we choose our factors, we choose the ranges that we want to investigate it. So that's the level of your factor. So how much reagent is there, how much water is there, time, temperature, pressure, things like that. So here we carry out an investigation. We find that two factors are important. And what we find is that so blue is low, going into yellow is getting higher. What we find is that these areas here are not very good. So the best area is here. And if we want to improve this process, we carry out additional experimentation in this region. So the first experiment will rule out the factors that are important and give us a direction of travel. We now have found the sweet spot for this process, and we can run a process anywhere within this sweet spot and achieve a very good outcome every time. So all of this is about understanding our process so that we can make informed decisions, and we choose the space where we want to operate based on the knowledge that we have here. Experimental design uses a lot of different terminology, and people call it different things. So DoE, design of experiment, experimental design, statistical experimental design, or factorial experimental design is all the same thing. And with all of this terminology, it's actually just a very simple and structured way to look at a cause and effect relationship between factors and the experimental outcome. So the factors, as I've already said, are whatever you might change. So your active material will be the same, but the additives that you have in there and how much additive will change. And we choose to investigate these because we expect them to have an effect on the outcome. So the outcome could be percentage yield for a reaction. It could be the availability or stability of your material. Experimental design needs and depends on very careful factor selection. If you don't investigate a factor, then you don't get the opportunity to improve the process for whatever that factor may have an effect on. So if you choose the right factors, investigate them in the right ranges, then you have a very good chance of developing a very efficient and robust process. So you need to identify which factors to change and over what range to investigate them. Experimental design will provide information about the whole system and how it works, because we're looking not at one factor at one setting, but we're looking across the whole process. And the important thing here, which puts many people off, is experimental design uses statistical methods. But essentially, you don't have to worry about the statistics. There are software packages that will do that for you in the background. But the statistical packages and the statistical techniques allow us to change all of the factors between each experiment and using statistics to determine the relationship between those factors. So if we're looking to develop a formulation, we will have a formulation which could be a tablet, it could be a capsule, it could be a liquid, it could be a solid blend. We'll have, so the different type of formulation we're trying to do will be important. What our bulking and caking or slipping agents will be. If we're tableting, what speed the tablet press is running at, what pressure it's applying. If we're looking at liquids, what solvents or additives do we have in there? So there's a number of different things that we could have. So for a formulation process, we have a wide range of factors, and I've listed some here to try and help you understand them in a bit more detail. So factors come in two clear types. Materials like the active ingredients, the binder, slip agent, bulk agent, disintegrants, surfactants, the type of equipment and the type of formulation, those are factors, but they're discrete. One exists, another exists, but it's often difficult to relate one material to the other. Then we have continuous factors like the formulation ratio or the particle size. We can choose a value and we can choose another value. And the only limitation from getting from one value to the other value is your equipment. So how much active you have present, what compression force, what temperature, mixing that you have, the spray rate that you have, all of those can be investigated. The number of factors will affect the number of experiments you have to carry out, but we also have responses. And some example responses could be the solution time, the solution profile, the strength of a tablet, the humidity stability, the active ingredient stability. So these are just some responses. Responses do not increase the numbers of experiments, but responses are very important because they're what will help us to understand how the factors affect our process. So for a formulation process, the option for the dosing form is a tablet, an ointment, a capsule, a suspension, a gel. If we wanted to look at more than one of these, we would probably have to look at this with a separate design for each one, because each of these different formulations may well have different needs with different materials that are being used in there. If we're looking at granulation, the particle size, the amount of binder, mixing, drying, these will all be important. If we're looking at tableting, so the compression force, the tablet speed, the tablet size, they will all be important. And if we're coating the tablet, that will also have an effect. So there's a lot of different things we could investigate using experimental design in a formulation process. So the problem that most of us have is that we're trained to think one experiment at a time. So we carry out one experiment and we move forward from there. So here I have something that I'm looking to carry out. In this case, it was a chemical experiment, but this could be exactly the same for a formulation. So we've never mixed these materials. We don't know how they're going to perform. So we choose a set of conditions and we carry out our first experiment. And as we know, our first experiment, or as we expect, our first experiment will rarely give us the outcome that we want. So here we're getting some material being formed, but it is not sufficient. In this case, with our knowledge of chemistry, we've chosen to increase the temperature. So we'll change one of the factors, and what you see is that the color for each experiment is changing, which is just meaning that we're actually getting more of our product here. And eventually, after you get more, you can then start to get a point where it then suddenly starts to degrade again. So at a higher temperature, you may start to degrade your product. So you get to a point where you're maximizing what you're getting, and then it can start to reduce again. So having investigated temperature and found the best setting for temperature, we now choose our best temperature setting, and we start to change the next factor. So we carry out a series of additional experiments. We carry out a series of additional experiments. We choose to go in one direction. We find that that's lower. We go in the opposite direction. We start to increase. And we're getting some slightly better results. And you know, our process is improving. We're getting better to what we need, but we're still not getting the full optimum of what ideally we would get. So one variable at a time, we've looked at one factor, we think we've got the best setting for it, we change the other factor, we think we get the best setting for it, and we get what is referred to as a local optimum. So we basically know the information that you see here, so you want to be at a certain level for temperature, you want to be at a certain level of concentration, but we really don't know how to make this process really work for us. Essentially what we have is the information that you can see here. There is a reaction profile, we have a little bit of information, but we don't really know what we could actually do with this. In actual fact, this is a profile of what this process can do, but from our OVAT study, we don't see this. So there is a sweet spot where we can get 100%, get exactly what we want, the perfect material, but we don't have that from working one variable at a time. If you use one variable at a time, the genuine optimum will most probably be missed. The experimental approach makes it almost impossible to find. It's a very inefficient use of resource. There are better conditions available. We've carried out, in this case, 11 experiments, and we have no idea where to carry out the next experiment to make the process better. We've carried out very limited, investigated a very limited set of experiments and the possible combination of design space. We have no information about how one parameter is affected by another, so we don't know if there's any interaction. And we have no idea on what the inherent variability is. So what is the experimental error? We got close to 40%. If we run the experiment again, will we get the same results? Will we be higher? Will we be lower? Experimental error is very important to understand the significance of the model. So if we use experimental design instead of one variable at a time, we still have the same factors. The difference here is we choose each factor and we investigate it at a low value and a high value. So here we have an experiment which is at low temperature and low concentration. Here we have high temperature and high concentration. So we create a design, we carry out 4 experiments, and what we find is that these 3 corners are all low. This corner is high. So we do not want to be in this area, we want to be somewhere up here. In this case, we choose to run a new design with this as our center point. So we carry out a subsequent design. And we find much more information. Now, some people will look at this and say, but you've carried out additional experiments and we are not now at our sweet spot. But the difference with experimental design is having used a statistical package to understand the factors and their interactions and other effects, we now have a mathematical model. And that mathematical model will predict the outcome for all of our experiments. So if we work one variable at a time, you carry out 11 experiments, you have 11 experiments worth of results. If you use experimental design rather than one variable at a time, we have the results from, in this case, a similar number of experiments, 9 with some replication will bring us back to 11, but we can predict the outcome of thousands of results. So any combination of these factors could be predicted what the outcome will be. And this will tell us where we want to operate our process. So experimental design is not really about working harder, it's about working smarter. Okay. So if we do carry out experimental design and we do this process properly, then it will tell us a lot of information. It will tell us what factors or variables affect our process or are important in our process. It will tell us at what setting or what level for those factors or variables we will get the outcome that we want. It will tell us which is the most important factors, which ones we need to pay most attention to, and will tell us if there are interactions between factors. It will also help us to understand where we need to operate this process so that we have a robust process with minimal variation. There is no point in having something that will give us a perfect material if it's not going to be something that we can operate reproducibly on scale, as in most cases we're looking for something to commercialize. It's also a very useful technique when you want to compare different suppliers or different grades of materials and see how they will affect the outcome of the process. So to get the most from experimental design, you need to avoid systematic error. So what is systematic error? The easiest one to think about is if you have a material that is hygroscopic or sensitive to oxygen and moisture. That material will change over time. So when you carry out an experiment today, you will get one result. But if that material then absorbs moisture or degrades because of oxygen, in a month's time, you'll get a different result. So if you're running an experimental design and it takes a month to carry out all of the experiments in your design, you will have different results from your experiment that was carried out today than you would at the end of the process if you're not careful. Because experimental design will have at least 3 experiments which are repeated, people know that they're going to see some error, and they are normally more precise because they tend to consider the variation in those experiments a reflection on them as a person and a scientist. It allows us to estimate the error in our process. So if we run a process and our first experiment gives us 75%, if we repeat that experiment and the next time we run it, we get 100%, and the time after that we get 50%, then we have a process that is giving us 75% plus or minus 25%. So this process is not reproducible, it's not robust, it's not something that we want to go forward with. If, however, the second the first one was 75, the second was 74, and the third was 76. You now have a robust process that you can really believe in. So it helps us to understand the significance of the model and how well we can trust it. Also in experimental design, because we're looking at a wide range of factors and ranges, we have something that should be valid over a broad range of conditions for a process. So how does experimental design improve the answers for us? The first thing is that if you want to get the most from experimental design, you need to carry out this process very carefully. If you go to the lab tomorrow and you carry out one experiment and you miss some important parameter or conditions and the experiment completely fails, provided you learn from that and the next experiment after that is carried out correctly and in the right region, then you've learned from that and it's not a problem. With experimental design, if you miss an important factor or you're not working with those factors in the right ranges and nothing works, you could waste a lot of material and a lot of time. So what you get out of an experimental design is directly related to what you put in constructing that design. So you have to think about the process, think about the factors and the ranges, the type of design you're going to do. So the attention to the design for choosing factors, choosing ranges, and carrying out the experiments and analyzing the data is extremely important. So to get the most from experimental design, we have to follow this DoE process carefully. The first step is to work out why you are carrying out the experiment. And so we want to define an aim. And we all want the perfect product for a few pence that is reproducible and reliable. But often the overall aim of what you're trying to achieve may well be more complicated than a single set of experiments. So for instance, then you need to set an objective. So for instance here, you want a formulation to deliver an active material in some format. But are you going to have a tablet? Are you going to have an ointment? Are you going to have a capsule? Each of these would have a different setting. So we use the objective to clearly set out what we're trying to achieve, and then being clear about that objective, we then go and start to select our factors and our ranges. So if we miss an important factor, then we're going to have poor reproducibility in our experiments, and we lose the ability to get the most from our process. So choosing the factors is really important. We then look over what range we investigate those factors is also very important. So the next thing that is really important is choosing the responses. How are we going to tell if changing these factors over the ranges we're investigating is having the effect that we want? It's important that you think carefully about the responses that you can measure and what you need to measure, because if your analytical data is not accurate enough, you may not be able to tell whether this factor has had an effect. So the variation between repeat experiments or the accuracy of the analytical data needs to be much less than the range as that we see in our results as we change a factor over a wider number of conditions. So having chosen the factors and ranges, having considered the responses that we want to investigate, we can go and choose a design. And we choose the design based on the factors that we have, the numbers of experiments that we need to carry out, and the objective we're trying to reach. So having chosen the factors and ranges, having chosen the design, we select it, we then go and carry out the experiments. We carry out the experiments and we gather the data. Now it's really important that we've looked at the right responses, because otherwise we could go through this whole process and then at the end find that there's another response that we wanted, but we've not gathered, and then have to repeat the design again to get the data. So after carrying out the experiment and analyzing it, we first of all check the results are making scientific sense. And this is really a check to make sure that something hasn't gone wrong in our experimentation, something hasn't gone wrong in our analytical, our some transcription errors in the data between whatever analytical instrument and us trying to analyze the data. When we're happy that the data is making some kind of sense and that the data is correct and accurate, we then go and model the data. The model data is carried out in any of a number of statistical software packages, and they will help to explain what's going on. They'll help to work out which factors are important, if it has a positive or a negative effect, if there are interactions, if there are other terms. The problem is, if you have an error in your data, the packages, the statistical packages, do not have the scientific background that we do, and it will just try and fit whatever we put in. So the checking results is important before we model the data. Every model will have a prediction at the end of it of where is the best place to run this process. Is it within the ranges you've investigated? Is it higher or lower values? We prove our model by carrying out the validation experiment, and that will confirm for us that the model is accurate. If that predicted and carried out validated experiment meets our objectives, our designs are finished. If it doesn't quite meet our objectives, it will at least have ruled out what factors are important, and it will have given us a direction to travel towards meeting our objectives. So if we need to, we can carry through this process again, taking all the information from the first design into a second and third design if necessary. If we carry out factor selection appropriately, and we investigate ranges in the right way of a wide enough region, then we would be expecting to run between 1 and at most 3 designs through this process. So it's just really important. I've talked about the DoE process, but it's really important to emphasize how much of this is about planning. What are you trying to achieve? What are the objectives? What ranges, factors, responses, design? All of this is planning. And there is a lot less in the do, act, and check. So when we're identifying factors, I usually use a wishbone diagram, and we look to consider every step in the process. So what order do we do things? What equipment do we use? What reagents or additives? What rates of heating, cooling, mixing? What grades of material? All of these are things that are important and should be considered as part of the process of identifying factors. When we're looking at responses, we need to make sure that we get enough of the right type of data to be able to understand how factors are affecting the outcome we want. So they should give you accurate and consistent results. They should replicate the outcome of the experiment. There should be minimum variation between them. We should minimize the experimental error between measuring the change to the factors and having carried out the experiment. If we have a lot of operations between carrying out the experimental change and measuring the effect, we can add a lot of error to this process and make it harder to understand. And essentially, the noise in the measurements, so what you get between your repeats, needs to be much less than the change in the results that you're going to get from the design. Okay, so essentially, there are different types of designs that you can use, and the most useful design type is a screening design. Usually, these are fractional designs looking to investigate a large number of factors over their ranges so that you can move to the appropriate levels to investigate. The second design type is around optimization. That's about taking the results from your screening design and trying to optimize your process. There are response surface designs, which are there if this process is going to be reliable and robust on a large scale. For formulation, there is another design type which is very important, and this will come in the screening and optimization part. Essentially, when you do a normal fractional factorial design, every factor is independent of each other. When we do a formulation, we're looking at components as part of a whole. We choose whatever that we want a certain amount of active in a material, and we don't want the mass of that material to be going, or volume of that material to be going up and down significantly across the design. So mixture design allows us to look at each of the components as a fraction of a whole. And it analyzes the response for both the mixture, so the components, and the process factors like mixing, temperature, and whatever else that you might consider as useful. And this design type uses a mathematical design called the optimal design. So a key deliverable for formulation is getting the amount of active material in a fixed weight or volume so that you then deliver the dose that you need to for whatever application that you have. Mixture designs allow everything to be varied while fixing the final weight or volume. It can be very hard to achieve with another design type. Okay, so just to demonstrate the difference between a mixture design and a fractional factorial design. Here we have three components. So we have A, B, and S. In a mixture design, the three components will always come out to the same 100% mass of material. So you can have very little or no A, you can have very little or no B, and the same for S. If you did a fractional factorial design and you investigated each of these factors independently of each other, then instead of everything coming out at 100%, we might actually have some materials which are 40% of the volume and other materials which are 160% of the volume. And then this would have an effect in how you investigate those materials. So the fractional designs are not appropriate if you're looking to have a mixture of materials in a formulation. So going to the case study, here we're looking at blending parameters and how they actually affect the uniformity of a material. So this is a pharmaceutical application, so some of the terminology may not be familiar to you, but we first of all start with a quality risk assessment. And this is looking to try and see what factors or parameters could actually affect the quality of the material. So we want the material, we want to deliver the right material and the right quality every time. So what could actually affect that? And this is the tabulating process using an active pharmaceutical ingredient or API. So the size of the material, the particle size will have an effect. The moisture control or content could have an effect. The blending and lubrication steps could have an effect. And all of these could affect the uniformity of the material. And if the uniformity of the material is not correct, then you're not going to end up with the right dose when you create a tablet. So a study of parameters to affect blending was conducted to help to develop and understand the design space. And the design space is just how all of these factors affect the process and where we can find that sweet spot that we saw in one of the earlier slides. The factors that were assessed and considered was the type of blender, the rotation speed, the blend-in time, and the particle size of the material. And the purpose of this design is to ensure that the blend is uniform, and we're using NIR. So we have the NIR spectrum, so near infrared of each of the materials going in. We have the NIR of the homogenized blended material. So there are differences, and what you're looking at is the changes of the individual components as they go to completely blended. And we use multivariate techniques to measure the change in this as you go from the three individual components to the single component. And they carry out a design, a DoE, to investigate this. So we have three factors here. We have 12 experiments. For the 12 experiments, we have a different run order to the experiment order. And this is to ensure that we don't have uncontrolled factors that are changing, like moisture content affecting the performance of material. So we have the blending time at a low value and high value, as well as the mid value. We have the RPM at a low and high value, as well as the mid value. We have two different blenders, the V type and the drum type, and we look at both as the midpoint. And we have particle size at low value and high value. Having created the design, we carried out the experiments and we get the uniformity, and we have a range of values here. So we're going to now move to analyzing the data. So the first plot we look at is the replica plot. So this is basically the responses on one axis. Each experiment is here across the bottom. In blue, we have the repeated experiments. So 9 and 11 are repeats, 10 and 12 are repeats. We see the green ones, which are the rest of the experiments. So the other high and low experiments, we see 2 give us a uniformity that is outside the range that's acceptable. The maximum that has been set is 0.01. 6 of our standard experiments meet our uniformity criteria. So we have 2 failures, 6 plus our center points, which all meet. Here in the bottom left, we have the coefficients. So these are the factors. And the coefficients plot is showing us the factors and how significant they are. Here we have the blending time. The blending time has a negative effect. So a low blending time has a negative effect. A high blending time should have a positive effect. Here we have RPM. So this is the RPM for mixing. The RPM low has a negative effect. So RPM high should have a positive effect. We have we have a squared term for blending, so it's a nonlinear response, and we have an interaction between blending and RPM. If we move up here to the top right, we have the summary. So the R squared is how well these factors explain this data. So essentially, we're able to explain 99% of the variation, or 99% of this experimental result is explained by the model from this. The blue bar Q squared is how well this model is predicted. And so here we have a very predictive model. So we predicted 98%. And essentially here, this is just to check there are no outlying experiments or experiments that are explained by the model, and all of the data is explained within 4 standard deviations. So if we then look at the interactions, what we see is that if the rotation speed is high, so here we have high rotation speed in blue, it doesn't matter how long the blending time is. But if the rotation speed is low, at a low blending time, we have a failure. So we can choose a low RPM with a longer time, or we can choose a high RPM and have any blending time. If we look at the next slide, we're looking at the contour plot, and here what we see is, with the black line, is where everything meets our objectives. The uniformity, we want it to be low. It's a heat map. It goes from blue being cold and low to red being high. So anything in this region is a failure to meet our objectives. Anything in this region meets our objectives. So the optimal conditions here are 30 RPM and 11 minutes blending time, and that will give us something which is very, very uniform. But anything within this space here will actually meet the uniformity objective that we set at the beginning. So the optimum conditions, we can get a value of 0.0025, but 0.1 was set as the target we must achieve. So we can choose where we want to operate our process. So in summary, the particle size and blended type are insignificant. The model explains 99% of the data and predicts 98%. Squared term is required. Some additional experiments can be carried out to confirm that. Uniformity of less than 0.01 is required. We can achieve 0.0025 if we wish, but we choose what we want to do. So hopefully what I've shown you, so the model identifies the important factors. The model identifies the setting for those factors. It requires a quadratic term and an interaction term to explain the variation, and it was very efficient. So here we've looked at 12 experiments to investigate all of these factors, and we now know where we can now choose where we want to operate our process. So hopefully I've shown you that DoE is a very powerful tool. You need to avoid certain pitfalls to make sure that you get the most from it. And the typical pitfalls that people see are in incorrect factor selection or missing an important factor, looking in the wrong ranges. If you range so you want to make sure that the ranges you investigate will achieve what you need to do. Inappropriate or inaccurate responses is something we see quite often. And then you want to make sure you validate the model. So when you carry out the validation experiment, that will confirm if your analysis is correct. So a good DoE will give you a lot of information about how the process will work, and you will get much more information from many less experiments. My experience is that I can do in a week or a couple of weeks what other people otherwise would typically take months to achieve. Okay. I think with that, I'll hand back to David.
Okay, I I'm not sure if everybody else is hearing it. We might have just lost Paul for a while there. So, but firstly, I mean, he was at the end, and thank you very much, Paul. That was a fantastic explanation of DOE in such a short space of time. I'm just going to remind everyone, it would be remiss of me if you found what Paul's talked about to be interesting, and I'm sure you would find it to be valuable if you are a formulator. Then we have a new 2-day training course, which we're running in December of this year in the East Midlands Airport in the UK. The cost of those 2 days is now £95 plus VAT if you register before.
Unmuted.
So David seems to be off air at the moment. The sound doesn't appear to be working. This is Jim Bullock, David's colleagues. I think at this stage, David was going on to say that on the 4th and 5th of December 2018, details on our website of a 2-day training course on design of experiments for formulators, involving, of course, Paul again for that. We do have time for 1 or 2 short questions. Paul, are you still on the line? Hello, Paul, are you still on the line?
I'm still here.
Yep, good.
Yes, I'm still here.
So we've got time for a couple of questions here. First question here is if I have to test the effect of formulation components and process parameters on certain responses, for example, granule size, should I build 2 different designs, or should I go with one design which includes all of the factors?
So I would recommend that you build one design, because the formulation components and the process parameters together could all combine together to have an effect. And most likely, they both will have an effect together. And if you try and investigate them as independent, as 2 separate designs, you won't get the full picture and lose the possibility of interactions. So I would definitely look at that as a single design, looking at both types. And mixture designs are perfectly able to do that.
Okay, that's fine. Thanks very much. Next question we have is how do you actually calculate the uniformity of the blend in that case study? What does the uniformity of 0.01 actually mean?
So essentially what you're looking at, so we're using multivariate analysis. We have an infrared spectrum of the completely homogenized blended material. We have the infrared spectrum of the individual components, and you use multivariate analysis to look at the small peaks that are changing very subtly as you go from the individual components to the completely homogenized blended material. And so a value of 0.000 is the completely homogenized. A value higher than that is that there is some of those components that are not completely blended and uniform, and you can still see discretely. So you're using multivariate analysis to look at that. It's not a simple calculation, but it is something that's typically done for this. So if you've ever used something like React IR to monitor a process or anything to do with this, that's what's going on, and you're looking at that change going from 0 to 100%.
Okay. Here's a question: what software is there available to carry out these designs of experiments? That'll have to be fairly brief.
Yes, there are a lot of different choices of software for this. The most important thing for the software is that it has replication. The software that I showed plots for is Moda from Umetrics, but there are other softwares like Design Expert, like Jump, like Minitab, and all of these work quite well too.
Okay, thank you. And the next question is, what are the importance of central points in a central composite design? Do we need 6 points or 2?
So the extra experiments in a central composite design. So central composite design is a response surface design. And so this design is looking for quadratic terms. It's looking for a nonlinear change as we go across the range for a factor. So your center points, the first reason you run a center point and run it multiple times is looking at your experimental error replication. Depending on the center composite design that you use, there are 3 or 4 different types. They will all help you to quantify and understand that nonlinear response. But if you use a CCF, you're looking at 3 levels for that factor. And so you get a certain amount of resolution about how that factor is changing in a nonlinear way. If, however, you use a central composite design, a CCC type design, you will look at 5 levels. So you will still only do one experiment 3 times, but you will then do additional experiments to understand that nonlinear response.
Okay, thank you. And then very finally, a point on question on the course on the 4th or 5th of December on mixture designs, only briefly touched on today, of course. How much coverage will you do you intend to give to mixture designs, specifically highly constrained designs or specific designs for screening mixtures with many possible components?
So we will have case studies looking at mixture design and looking at different types of designs in formulation. There are a number of case studies that will be presented through this. And we will try, if you come with a problem, we will try and create a design for you.
Okay, so thanks very much, and thanks very much again, Paul, for a really comprehensive overview of the subject, and thanks everybody for their questions and for your attendance today. The full set of slides will be made available to you, as will the recording for this webinar, and the full set of slides does have some information and some links on the course, as well as some contact details for ourselves and for Paul. So thanks once again, and we look forward to hearing you again at one of our future webinars. Thank you. Bye-bye.